Oh, good afternoon. This is Mr. Precella. We're going to continue working the review for the Math 13-14 final exam. Remember, in this course, you have two finals. You have the final quiz for the foundations grade and the final exam, the 13-14 final exam. This is the one that's the most important. It's also the one that's longer and the problems are harder, I guess, but that makes sense. We worked problems 1 through 5 the last time. So the last problem we did was a cut point problem, an inequality. So let's look at number 6. Okay, well, switch over to my paper.
Oh, you've already written?
I wrote it down earlier. So when we see an inequality, that makes us think cut points. There are two types of cut points, solution cut points and denominator cut points. The previous problem, number 5, there were no fractions in the inequality, so there were no denominator cut points. But here, the inequality does have a fraction, so we'll have to worry about those denominator cut points. But the first thing I'll do is find the solution cut points. The solution cut points occur when the left side equals the right side. So we set the the inequality equal. And what do you think I'm going to do to solve this equation? We've been very consistent. If we had an equation with a fraction, what would we do? Okay, so we can treat that 3 as a 3 over 1. I should have written it smaller. And then we'll cross multiply to get rid of the fractions. So that's what we've been consistent about. If the equation has fractions, we multiply through to eliminate the fractions. So we go 1 times x minus 15. Well, 1 times anything is just the anything, so we just have x minus 15 equals. Now we're taking 3 times x minus 46. What's that going to give us? Okay, 3x. You're distributing the 3 minus 3 times 16 is 48. I think, notice this is linear. There's no x squares. We're not going to have to try to factor or anything. So we just need to combine the x terms. I think I'm going to get all the x terms on the left side. We have a 3x minus 1x. That'll give me a 2x. What am I going to do to get rid of that minus 48? Add 48. Negative 15 plus 48. Is that giving me a positive 33? Then we divide both sides by 2 to get x equals 33 over 2 for my solution cut point. Solution cut points, sometimes they're open circles and sometimes they're closed circles. What do you look at to make the decision? Okay, if there's equality, then use a closed circle. This 33 over 2 makes the left side equal the right side. Well, equality isn't allowed here, so this solution cut point will be an open circle. Denominator cut points. You don't have to look at the inequality. Denominator cut points are always labeled how? Denominator cut points occur when the denominator is 0. Do you ever want to make a denominator equal 0?
So you just do x minus 16 cannot equal 0.
Okay, that's right, but I was getting at was the open circle, okay? So, but you're right. We're going to take x minus 16. We don't want it to be 0. That means that x cannot equal, okay, for my denominator cut point. Now we'll draw a number line. We have two cut points. Which one's smaller? The smaller one, well, they're both going to be open circles, aren't they? They're both open.
The 16 is smaller.
The 16 is smaller. 33 over 2, that's 16 and a half. So that's larger. And notice there were no even multiplicities, no even exponents. If there's no even exponents, the only linear terms, then you can be confident that the intervals are going to alternate, either true, false, or false, true, false. So you can check all three intervals, but I think I'm only going to check one. What number do you think I'm going to test? 0. Which interval contains 0? Interval 1, 2, or 3? Interval 1. So I'm testing 0 here. That's going to give me, I'm testing it in the original problem. 0 minus 15 is negative 15 all over. 0 minus 16 is negative 16. Is that bigger than 3? Negative divided by negative, that's a positive 15/16 is bigger than 3. Certainly not. That number's less than 1, so that cannot be true. So we cross that out. If we had tested a number between 16 and 16 and a half, something like 16.1, what do we expect to happen? Shade or cross out? Shade. And here? Okay. So, our final solution written using interval notation. We have an open circle, so a parenthesis, 16, comma, 33 halves, another open circle, so another parenthesis. Any questions there? So we come over here, an open interval, so I type the parenthesis, 16, comma, 33 halves. Get out of the denominator before you type your other parenthesis. Move this way over here and say, check my answer. Any questions there? Okay, number 7. Find the center radius form of the equation of a circle with center at 3, negative 3, and radius 7. So, number 7. It's a circle. I'm just writing down the important information. Centered at 3, negative 3, and radius of 7. Remember center radius form, x minus h quantity squared plus y minus k quantity squared equals the radius squared. They use the letter h to represent the x coordinate of the center. They use the letter negative 3. They use the letter k to represent the y coordinate of the center. So we have x minus y minus. So in place of this h, we write the positive 3. In place of the k, we write the negative 3. And what's going to go here? The 7. And we can clean this up a little bit. X minus 3 squared, we're just going to leave that as x minus 3 quantity squared. Plus, what about that minus and negative? What's going to happen there? Okay. And 7 squared is 49. Notice something. We would have stated, we'll go ahead and type it in first.
Go ahead and finish up.
I just wanted to mention that. We would have stated that what you see inside the parentheses is exactly the opposite of the center. For the x-coordinate, you see a 3. Inside the parentheses, you see a -3. The y-coordinate of the center is a -3, but inside the parentheses with the y, you see a +3, because the way the minus from the formula combines with that negative to change signs. And now we have to remember how to use the circle graphing tool. Pop out the little palette, and then you choose the tool. Remember, if you come right up here and expand that, I'll try to give you instructions. Click the tool you need. Well, this is a circle. And then it says plot the center. The center was 3, -3.
Upper right-hand corner of the yellow rectangle tells you the point you're at, 3, -3.
Now we need it says to plot one other point. Well, to get the other point, that's where you use the radius. The radius is 7. So you count 7 units from that center. You can count it any direction you want, okay? But what are you doing? Okay.
If I started at -3 and moved up 7, I would be at 4, and that's what the point is. 3, 4. Click.
Save it. Oh, I've lost the mouse. Where's the mouse? The cursor.
Or that arrow. There
Oh,
it is. I saw it. Right
there.
You said 3, 4.
We were at -3 plus 7 drops us at -3 plus 7 gives us a y value of 4. Or you could have been at 3 plus 7 would drop you at 10 if you moved horizontally. Number 8.
Another one.
But they didn't tell us the
another
center and the radius here, did
wow.
they?
This one's more involved. We're going to have to rewrite this so it's in that parenthesis form, the center radius form. X minus h squared plus y minus k squared equals r squared.
Okay, make sure I didn't miscopy the problem. X squared plus y squared plus 8x minus 2y equals 19. There. So, we need it to look like this. Because remember, I said with center radius form, we know how to find that center. Just change sign, change sign. What do we do to this number to go back to the radius? You're undoing the square by doing what? Take the square root. So I think what we do is we'd say, okay, let's group the x terms together. X squared plus 8x plus, and we'll skip some space. Then we have the y squared minus 2y plus skip some space. And we have that 19 on the right-hand side. This process only works if the leading coefficient is a 1. If we have something other than a 1 as the leading coefficient, we have to divide through to change it to a 1. What's my leading coefficient?
Aren't you supposed to put a space on?
Yeah, I was going to go.
Oh, okay.
Plus a black space and plus a blue space. Oh,
there. I just add them over there. Tony's the one that draws the spaces, okay? Tony draws the spaces, okay.
Continue on.
Well, now, leading coefficient, what have we got?
1.
A 1, so we don't have to divide. You take that number, the coefficient of the unsquared variable, you do two things to it. What do you do first? To figure out the number that goes in the blank. Okay, so you take, here's my scratch word, you take the 8 divided by 2, that gives you 4. 4. And then you square it. 4 squared is 16. So you add the 16 here, but to maintain the equality, you have to put 16 on the other side, or add 16 to the other side as well. What are we going to put into the blue blank? I couldn't hear you? 1, I agree. You take that number. You don't have to worry about the sign because you're going to square the result. That's going to give you a positive number anyway. I just take the number part. Half of 2 is 1, and then 1 squared is 1. So we add 1 to the left and 1 to the right.
Right half is equal to 36.
Okay, that 19 plus 16 plus 1, I agree, that's 36. We need to factor and factor as perfect squares. We should have two perfect square trinomials here. Okay, it's a variable, sine, half of that number. X plus 4 times x plus 4. If you FOILed that out, you'd get back x squared plus 8x plus 16. Now the y's. I agree, y minus 1. Remember, it's a variable, sine, half of that number. If you took y minus 1 times y minus 1 and FOILed it out, you'd get back y squared minus 2y plus 1. So you can determine the center. Okay, so it's the opposite, negative 4 and the radius. Okay, you square root that constant to give you 6. So the center is negative 4, 1. The radius is 6.
And I think all we're going to do is graph it.
Oh, you're right. I thought they...
Yeah. So, expand, circle. What was that radius?
The center was negative 4, 1.
Center. Negative 4. Ooh, look at how these are incremented.
They're incrementing in units of 2, so be careful.
Am I at negative 4, 1?
Look in that little yellow
rectangle.
Yes. Okay.
And now what's the radius?
6.
So starting here, I'm going to move. I'm moving right so that it'll be
I would have just moved up.
No, because
1 plus 6 is 7.
Oh, I'm going to go 2, 4, 6.
7.
Oh,
the radius is 7.
You wrote down 6.
Oh, it is 6. You're right. Where did I get 7 from? Okay. Yeah. Okay.
But maybe I'm not at. Did I move over 6? This is
No, negative 4 plus 6 should be 2, 2.
No, 2, 1. 2, 1.
Okay.
Okay, the radius is negative 4, 1.
Moved over 6.
2, 4, 6. So that other point is 2, 1. I don't like it when those boxes aren't incremented just one.
It makes it.
Yeah.
Screws me out.
But something else, what we're doing right now, if I could see myself 35 years ago, I'd be like, what sort of science fiction mumbo jumbo is this? Drawing these graphs on a computer. I guess that's a computer, but I don't know where the mainframe is. Where's the Honeywell CP6?
Where's just that big box?
Where's that huge box, you see?
Right.
So, yeah.
Okay. So are we ready for the next one? Any questions on this? Okay.
Find the domain of the function. That's something
It
that's
says do
short.
not use a graphing calculator, but if you want to do it with a graphing calculator, more power to you.
I can't imagine anyone wanting to do it with a
I don't
graphing
think that would
calculator.
be easy. If you want to do it in a harder way, then go for it.
Okay, so they want us to find the domain. Okay. Okay, so they give us a function, they ask us to find the domain. Well, we see that it's a fraction. We see that it's a fraction. We know there's something we don't want to have happen when dealing with fractions. It happened on number 6. What do we not want to have happen to fractions? No.
You don't want a zero where? Where do you not want the zero in a fraction?
A number over 0. What does that say?
No.
No, you can't do it. So you don't want the denominator to be 0. It's just not finding those denominator cut points on number 6. Just set that denominator not equal to 0. Well, we're going to have to factor this. We could use the quadratic formula, but I think it's factorable without too much trouble. X and x. The last sign's a minus, so what does that say? I couldn't hear you. A plus and minus, I agree. And now for 6, there's not many possibilities. 1 times 6 or 2 times 3. And we would use 2 times 3 because with a simple trinomial, you choose the pair that adds, in this case, subtracts to give you that number there. So play around with it. In order to get back a minus 1x from the outer and the inner, where do we need the 2? Where do we need the 3? What should go here?
X plus 2 and then x minus 3.
I agree. Y'all need me to FOIL that out to verify it, or do y'all see it in your head? Okay, so x plus 2 can't be 0. X minus 3 can't be 0. So x cannot equal negative 2. Good. And x cannot equal 3. So x can be anything else. If we were going to write the domain out in words, I'd say all real numbers. Right.
Mm-hmm.
All real numbers.
Do it back in the olden days.
Except negative 2 or 3. Could you plug in 50 million for x? Yeah. Could you plug in pi for x? Only numbers you can't plug in are negative 2 and positive 3.
Let's see. Oh, yeah.
So, but they're going to want the they want us to write the domain in interval notation. Notice the instructions there. So how do we write that in interval notation? I always think of a number line. I picture it on a number line. You don't want negative 2 and 3 are like those denominator cut points. You don't want them to be used, but they can use anything else. You can use all of those numbers, the numbers between negative 2 and positive 3, and the numbers to the right of positive 3. So how do we write that using interval notation? Are we going to have any rectangular brackets in the interval notation? No, so it's all going to be parentheses.
So parentheses, negative infinity, comma, negative 2, union.
Wait. Parentheses, union.
I'm writing as I'm talking.
Okay, keep going.
And then it would be negative 2, comma, 3.
What goes in front? Well, we've already said everything's going to be parentheses, union.
And then it would be the parentheses 3, comma, infinity. Oh, no, I didn't mix up with the negative. For some reason, on the first one,
never use that. Infinity. I'll go tab, but okay. What is it? -2?
-2.
Oh,
Oh.
shoot.
You got to get into the blue dot space. -2. That's not much longer than just typing the parentheses. Union.
Parentheses. -2, comma 3, close parentheses, union, parentheses 3, comma, infinity, close parentheses. All of that just to say all numbers except -2 and 3.
And look back here. I want to make a note of this because it's probably the last time I'll be able to. Notice, everything is shaded on the number line. The only numbers that are not shaded are -2 and +3.
And they're not shaded, that's what the open circle means. It's not shaded.
Okay, number 10.
Another domain. Now's your chance to say it. Okay, when you said it a while ago. What do we not want on square roots? We don't want
Oh, negative.
negatives. Huh? We don't want negative numbers under that square root.
F of x equals the square root of 16 minus 2x. And they want us to find the domain. Okay. There it is. If it's a fraction, we don't want a denominator of 0. If it's a square root, there are two things you have to avoid when you're finding domains. There are two general things to avoid. You have to avoid that denominator of 0. We saw that in problem 9. The other thing you have to do, you avoid square roots and negatives. Because if you have a negative number under a square root, you get an imaginary number.
That almost looks like a fraction bar. Right, negative or NEG.
Oh, I guess it does. Okay, NEG. Well, I'll write it like that. You want to avoid denominators of 0. You want to avoid square roots and negatives. So when you see a square root, you think to yourself, 18 minus 2x, it can't be negative. Could this thing under here be 0? Is it okay to have a 0 under a square root here? What would be, if that was equaled 0 underneath, what's the square root of 0? 0, that's fine. So that has to be greater than or equal to 0.
The square root of 0 is fine on a calculator. The square root of a negative number, we know that the square root of -4 is 2i, but we want only real numbers, so no negatives.
This is an inequality. To solve an inequality, we have been very consistent this semester. We use cut points. First thing we do, we ask ourselves, when does 18 minus 2x equal 0? And I'd move that 2x term over by adding it. Divide by 2. What am I getting for my solution cut point? 18 divided by 2 is 9. So that's my solution cut point. How am I going to label this on a number line? The solution cut point. I've got mighty quiet. Solution cut point. Equality is acceptable, so I agree. Close circle. We draw a number line. There's 9. 9's going to be included. It's a closed circle. Negative infinity and a positive infinity. Oh, by the way, I forgot to mention denominator cut point. Are we going to have a denominator cut point? No, because there's no denominators. As soon as, when you're finding the domain of a square root expression, as soon as you write it as an inequality, I don't look back at the original problem. I pretend this is just a cut point problem. So there's no even exponents. So it's going to either have to be true, false, or false, true. How will we decide? Okay, which interval contains 0? Interval 1 or interval 2? Okay, so we're going to test 0. That's going to give us 18 minus 2 times 0 is 0 is greater than or equal to 0. 18 is bigger than 0. True or false? True. So that means we cross out. If we tested 10, it would have been false. And then we write the interval notation representation. So call it out. What would I type first? Parentheses, because you always put a parenthesis in front of a negative infinity. Common 9. What's going to go after 9? A bracket, because you have a closed circle.
Negative infinity, comma 9. Negative infinity, comma 9. This bracket, right there.
For the domain of square root functions, I set up a cut point problem. Either it's greater than, the thing under the radical is greater than or equal to 0 if the thing isn't in a denominator, or number 11. Surely number 11 is going to be one. Oh, well, okay, that's it.
Okay. Two domain problems is enough.
Yeah. Okay. Number 11. Oh, it's graphing a piecewise function, and you'll notice it's multiple choice. We'll use the y value equal 3 for x values greater than or equal to 1, and it'll equal negative 4 minus x for x values greater than 1.
Less than 1.
Oh, yeah, less than 1. Less than 1. Oh.
So 3 for x greater than or equal to 1, negative 4 minus x for x less than 1. Good.
And what we would do to plot, to draw piecewise functions is plot points, but we plot the points intelligently. Y equals 3. Y equals a negative 4 minus x. There's no exponents there. These are just lines. I guess they would each be classified as rays because it's just half a line. But we're going to make a table of values. I'd call the number or numbers that appear in the inequality, I'd think of them as cut points. The blue graph is going to change to the red graph at 1 on the x-axis. So when you draw that xy grid, here's your xy grid. I'd start off with I'll make a table of values for the first piece. Here it is. I'm making a table of values. The first number I must use in this table of values is the number that appears in the inequality. I've got to use a 1. That's my cut point. Now, we'll use the same rule for solution cut that we use for solution cut points when it comes to labeling the starting point. The equality is acceptable. X can equal 1. So this point here is going to be a regular closed dot. We need another x value, a number bigger than 1. What do you think I'll use? 2? Now, any secondary value that you use has to be a closed dot. You can't choose a number. You can't say, oh, I'm going to use 0 for this. You have to choose an x value that's greater than 1. So the secondary point you choose has to be a regular closed dot. The only time that you have to worry about open and closed really, or when you're plugging in, when you're using the cut point themselves. In both cases, what will the y values be? 3.
This is called a constant function.
So we go right 1, up 3. That's my starting point. Then we go right 2, up 3. The graph starts at the cut point. Now, this is a line. Y equals 3. It's a horizontal line. Connect the 2 dots.
This blue might be better. Maybe
Oh.
it's time to retire this blue.
Oh, I thought it was working pretty good.
Oh, okay.
Any questions on that portion there? Now the red piece. This is piece 2. So that was table 1. Now we're going to make table 2. What's the first number I must use for x? 1, but notice there's no equality. That just looks so bad. I'm going to rewrite it. X less than 1. Notice there's no equality. So how will I label the starting point?
Open or close?
Open, because there's no equality. I need another x value, one that's actually less than 1. What do you think I'm going to use? 0? Of course, I'm going to use 0. Is this going to be an open circle also? No, because 0 is less than 1. You can't have these open circles just floating all over the graph. Any number that you choose on your own has to satisfy the inequality, which means it has to be a regular closed dot.
Okay.
Plugging in 1.
I just have a really quick question about using 1. Doesn't it have to be equal or with the triangle with the line? Oh, I'm sorry, with the,
But 1 isn't included in this function, but 0.99999.
0. I remember talking about those infinitely many numbers that to the naked eye look like 1. Let's just draw the graph and then I'll make that point, okay? Why did we start with 1? Do y'all understand Caitlin's question? It's a sensible question. If x can't equal 1, why are we plugging in 1? Well, we'll answer that in a minute. Negative 4 minus 1 gives me a y value of? Plugging in 0. Negative 4 minus 0. So we go to 1, negative 5. We go to 1, negative 5, and we have an open circle. Then we go to 0, negative 4. That's just a regular closed dot. Any x value that you choose on your own has to plug in, has to be a regular closed dot. So let's, first of all, choose the graph. Well, let's go back over here. Let's look back. X can't equal 1, but the real number system is dense. I claim that there are infinitely many numbers right there on the x-axis that look like 1.
0.99999.
0.99999. If you were going to use 0.99999, and I told you, point to that number on the x-axis. Where would you look like you're pointing? It would look like you're pointing at 1. So there are numbers that satisfy that condition. They're less than 1, but to the naked eye, they look like 1. And so that's why we plug in that 1 and put that open circle. That's saying 1, negative 5 is not on the graph, but there are infinitely many numbers
that look
that
like
look like 1, -5 that are on the graph.
Now, let's
A, B, C, or D?
Let me see. I'm going to see. I'll pop out this one.
Oh, no.
No.
That's
I almost-
close.
See, I think the open and closed are wrong there. So which one is it?
D.
D? This one? Is that it?
Yeah, the top one's closed, the bottom one's open.
Mhm.
Yes.
Okay.
This
So,
box D.
D. Any questions over this? If you can graph a piecewise function, you understand a lot about graphing. A lot. Let's see. What's next? Those difference quotients.
How about we take a small break, Tony, and then we'll pick up here in a moment.